All right. Good morning. Let's start the lecture here. Let's continue on a second order ODE. This is what we did in the previous lecture. So we have looked at the solution to second order homogeneous linear ODE with constant coefficients. Basically, we have looked at the equation like this. So here's the second order linear ODE and homogeneous. The coefficients for the second order ones here are constant. So A and B, they are constants. Now this equation could be given as, A, B, and C. It could be like this, which is actually what I gave it to you in the handout, the one-page handout. But when you have this, when you divide it by A, these two basically interchangeable. So when you divide it by A here, then you get back to the first one. And what we do is we said, we want to find a solution for this one. And we essentially look at three different cases. So first, to get the characteristic equation. Characteristic equation is you replace the second order one with the second order equation, quadratic equation, lambda squared plus A lambda plus B. And then solve for this one here. And now the solution of this characteristic equation guides us into three different cases. So three different ones. The first one is when you have two distinct roots, distinct real roots. Because the solution of a quadratic function, has two. The first one is two distinct real roots, lambda 1 and lambda 2. Then your general solution, is y equal to c1 times e to the power lambda 1t and c2 times e to the power of lambda 2t. And case number 2, when you have two repeated roots. Or in other words, there's only one root. So basically just the lambda here. But the lambda repeated twice. That's when you have two repeated roots. Then in this case, your general solution is y equal to c1 plus c2 times t and e to the power of lambda t. So lambda is the root. So this is the case number 2. Now in case number 2, let me extend this case number 2 a little bit here. Lambda, in this case, if this is the characteristic equation, lambda in this case is a over 2. So negative a over 2 is the lambda. So let's take a look at the situation, the a value here. If a value is greater than 0, so a could be less than 0, but let's consider the case when a is greater than 0. If a is greater than 0, then you can see in the solution here you have what? This is basically c1e negative a t plus c2t e a over 2 times t, right? Okay. The first term is e to the power negative a over 2t. So if a is greater than 0, then as t approach to infinite, we are guaranteed that this term will go to what value? As t go to infinite, this term should be, what should that be? 0, right? Yeah. So this term will go to 0, that's for sure. But what about this term, right? The second term. The second term, and you know this is going to go 0. But however, as t go to infinite, t will go to infinite, right? So now you have a dilemma. So you have an infinite times 0. Then what should that be, right? So what we do is, okay, we can use this L'Hopital rule here to actually verify what will this term go to as t go to infinite. Okay. So we can try this as t go to infinite. Let's take a look at the limits for this t times e to the power of lambda t. And that is the same as t over e to the power of a over 2 times t. Right? It's a negative here. So the L'Hopital rule says what? The limit like this is equal to the limit when you're taking derivative of both the numerator and the denominator. So the numerator's derivative is 1, and denominator's derivative is a over 2 and then e over 2t. So as t go to infinite, this term will actually become positive infinite. So 1 over positive infinite, it should be 0. Right? So this shows you t times this as when a is greater than 0, the second term will also go back to 0. So in other words, as t approaches infinite, then the y will approach to 0, right? If a is greater than 0. Okay? Yeah. It's exponential. So I'll show you after this one called homogeneous response. The essentially idea is this is a stable response. Okay? So it will go back to 0. That's why it's stable. If it starts to explode, then it's unstable. Okay. That's case number 2. Okay. And case number 3 is when you have 2 complex conjugate roots. 2 complex conjugate roots. So 2 complex conjugate roots. Okay. In this case, right, if my characteristic equation is this, okay, then your lambda 1 and 2 is this. But you can always write it, okay, as 2 complex conjugate roots in general. So alpha plus minus j beta. Okay, that's your lambda 1 and lambda 2. So you can see lambda 1, let's say, equal to alpha plus j beta. Lambda 2 is alpha minus j beta. Okay. So 2 complex numbers. If you have 2 complex numbers, theoretically they are distinct from each other, right? So you can form your general solution as y equal to c1 e lambda 1t plus c2 and then e lambda 2t. So you could form your general solution like this. However, as I pointed out in the previous lecture, when you form your general solution like this, and you know your lambda 1 and lambda 2 are complex numbers, but your y has to be a real function, right? So that means c1 and c2 will not be a real constant, and they will also be a complex numbers. Okay? Yeah. So y has to be real, right? Y has to be real. So that basically means C1 and C2, they are complex. So it has to be complex here. So that does pose a question here. This is not really what we like. Okay, what we want is a real solution, right, for Y. Okay? Explicitly real. Okay, not like a complex numbers. Okay, in the solution net here. Okay. So then how do we get it? Okay, so let's show you how can we get a real general solution. Okay. So get back to this. Okay, the two solutions that are here. Okay, so if you look at this, we have two particular solutions. One is, let's call it y1a. So y1a is e to the power of lambda 1t, and the other one is called y2a is lambda 2t. Right, those are the two particular solutions. And then you multiply by a general constant C1, C2, you get the general solution, right? Yeah. So the first particular solution, if I plug in lambda 1 into this exponential function, lambda 1 is alpha plus j beta. So we get e to the power of alpha t here. And then inside is cosine beta plus j sine beta. And this one here, you get e alpha t cosine beta minus j sine beta. Okay, so those are the two particular solutions. Okay, they're complex. Okay. So now I want you to think back. Okay, in the actually was the last lecture or two lectures before. If y1a is a solution and y2a is a solution, there is one theorem, actually theorem number 1, right? So if y1a and y2a are solutions, okay, then I can also see that y1a plus y2a divided by 2 is also a solution. Okay, right, that's one of the theory. Basically, linearity, right? Superposition here. Yeah, when you have two solutions, as long as you apply the superposition rule, then you still get a solution. Okay, out of this. Yes.
So why would you divide by 2?
That's right. That's why you will see y divided by 2. Yeah. So let's take a look at, right, what happens when you calculate this plus this divided by 2. So let's take a look at, if I add these two, okay, if I adding these two up, what do I get? You have a positive and negative right here, so you will add these two up, the j term gone, right? And you're left with twice of the first term. And then you divide it by 2, basically get rid of that 2. Right? So basically your 1/2 y1a plus y2a. Okay, let's call this is y1. Okay, let's call this y1 here. So that gives me e to the power of alpha t times cosine beta. This is a solution. And this is a solution that does not involve complex numbers. That's making use of the theorem. Not enough, right? So when we form a general solution, we need two particular ones, y1 and y2, to form a general solution. And the y1 and y2 has to be linear independent of each other. So what else can we do? I could also do this. Well, if y1a and y2a are solutions, again, right? I'm using the fact at here. Then y1a minus y2a divided by 2j is also a solution. very much like the previous one, except this time you're dividing 2g, right? 2g is still constant. It's just a constant complex number. Okay. It still satisfies the superposition, basically. So now, if you look at this, and then what is, so let's call this as y2. So what is y1a minus y2a divided by 2j? This gives us e to the power of alpha t. So if you look at this, so the first one minus the second one. First one minus second one. So this is a common term. They cancel out. Plus minus positive minus minus, you get a positive. And then you get basically 2 times j sine beta and then times e to the power of alpha t. Okay, so that gets sine beta. And then you divide it by 2j, you get rid of the coefficient 2j. So this operation here, okay, these two operations give you another two particular solution. But the good thing is, these two particular solutions, they are all real now. And they're all real functions. And this is good. And the other thing is, if you look at these two solutions here, the two new particular solutions, one is cosine, the other sine, and they are linear independent of each other, right? So they are linear independent. So you cannot express one using the other. So that basically means I can form a general solution using y1 and y2. So now I can form a general solution. Let's call it y. So c1 times y1 plus c2 times y2, okay, which is c1 e to the power of alpha t, okay, and cosine beta did I miss a beta t here? Yeah, sorry. So this is beta t, right? Because it's alpha, lambda is alpha plus g beta, so alpha t plus j beta t. Okay, so I missed the t here. T and t at this. Okay. And then here you get e to the power of alpha t beta cosine beta t and plus c2 e to the power of alpha t and sine beta t. Yes?
So what are those constants? C1?
Now this is C1, C2. They are not complex constant anymore. They are just arbitrary real constants. Right, so C1 and C2, they're just real constants. Yeah. You can find C1, C2, right, based on initial conditions. Yeah. Okay. Now in the lecture notes writing, sometimes to differentiate this case, instead of writing C1, C2, I use another set of symbols called A and B. So use A and B instead of C1, C2 for the writing here. So which is fine, it's the same thing. Okay. So that's the general solution for case number 3, when you have two complex conjugate roots. So 3 different cases. And I'll give you a handout. Okay, now the handout has a table. This is actually, if you call the formula sheet, you actually can bring this in the final, okay? And you just have to use this table to generate your general solution. Okay. For this particular one at here, okay, you could rewrite y, take out the common factor e to the power alpha t. Then inside here you get a times cosine beta t plus b times sine beta t. Okay. What's in the bracket Okay, what's in the bracket? Yes.
So like on your sheet,
Yeah.
I'm noticing like, so you're saying alpha equals negative a over 2 and beta equals square root b minus a squared over 4. On here, alpha and beta have been given different values.
Yes, yes.
Why is that?
The reason because I use lambda squared plus a lambda plus b as the characteristic equation. So you see here, this is in my lecture notes. I used a simpler second order linear ODE with constant coefficients. So I don't have this number here, right? The reason they are actually the same, because you can always divide these constants by both sides, then you end up with this equation here. You see what I'm saying, right? Yeah. So it basically in the table, right? In the table that gave it to you, the a value is 1 in my case set here. Yeah? Yeah. So it's the same thing basically. Yeah. The table, you can consider this table as a little more generous, right? A little more generous because my here is a equal to 1. Okay. It's like I did a standardization first. I normalized this to 1, right? Yeah. But it's the same thing. So whatever second order differential equation you're given, you're still going to write down the characteristic equation. You're still going to calculate the roots. And you could normalize this equation first by dividing the coefficient, make it a 1, right? But you will get the same roots, basically. Yeah, doesn't matter what you do. Because it's 0 here. Yeah. Good question. Is that clear? Yes. Good. Excellent. Okay. So the third case, okay, so generally my expectation if you end up here, then I'm fine, okay, so you're not going to get any point deducted, so that you get full mark if you get it right up to this stage. However, okay, you can certainly simplify the term inside the bracket with one more step. As you actually recall that when we learn complex number, we use the phasor, right, to simplify addition of two sinusoidal signal with the same frequency. Okay, we did that. So this essentially falls into the category. This is cosine, this is sine, but you can always write a sine into this. You can always write a sine into cosine. So now you have the same frequency, right? And it's addition of two sinusoidal signal. So you can combine these two together. To combine these two together, there are many different ways. In my lecture notes, I think I showed you at least 3 different ways to combining these two terms together. But irrespective whichever you choose, okay, you could always write down the addition of this cosine beta t, sine beta t with a and b at here as this. Okay. You can always write down this as this. The magnitude becomes square root a squared plus b squared. Frequency is not changing. And then there is a phase angle phi. The phi is equal to inverse tan b over a. The phi is always between negative pi to pi. Okay. So I'll consider this is optional, but I would highly encourage you to look into the lecture notes as to how you can write the addition of two sinusoidal with the same frequency into this kind of general format. There are different ways of doing it. There's one way is actually using dot product, kind of reviewing the material that you learned in the other course. Okay, and the other way of doing it is using the phasor concept. Okay, but just remember in exam, I don't necessarily require you always to write this into this. Okay, as long as you end up here, then you're fine. Okay. but it's a good skill to have, especially when you're playing basically lattice circuits, and you have one input and another input, and then the oscilloscope will actually add these two curves together, show you another curve, and then you can actually explain why the resulted curve, right, using this formula here. Okay. So those are basically the three different cases. Okay, you have the table there, 1, 2, 3. So whenever you have a question, you got to resort to the table and find the right answer. Okay. So let's take a look at a few examples. Okay. First, let's take a look at this one. Solve y double prime plus y prime minus 2y equal to 0. Initial condition is y of 0 equal to 4 and y prime of 0 equal to negative 5. Okay. The first step, when you deal with this kind of equation, look into it and you find this is 0, so it has to be the homogeneous. And then you look at the coefficient, they are constant, so this is exactly what we just have done. First, write down the characteristic equation. Lambda square, lambda minus 2. Okay. And you can always using the formula to get the roots. There's nothing wrong with that. But I think often in time, what's even faster is you can look at it and see that you can actually factor this quadratic equation into two terms. Okay. I think this is actually grade 10 stuff. Yeah. Right. How you do this, right? There's different ways. You basically sometimes manipulations, try and errors. You get how to factor into this. Okay. If you're not comfortable with this, then use the formula. Okay, it's the same thing. So that basically means for this one, I get two distinct roots, and one is negative 2, and the other one is 1. Okay. One of the common mistake in the student work is, you know, they often miss a negative, okay, when there should be a negative. Okay. Once you get this, and then you look at the table, because there are two real roots, so your general solution is C1 e, let's call this is alpha 1, lambda 1, lambda 2. So C1 lambda 1t plus C2 e lambda 2t, and C1 e negative 2t plus C2 e t. Okay, that's your general solution. And then we'll make use of the initial condition to solve for C1 and the C2. Okay. So to solve for C1, C2 unit initial condition, you can see that when you substitute t equal to 0, your y should be 4. Right? So y of 0 means what? Means when you substitute t equal to 0 at here, you get C1 and C2, but overall this should be 4. So that's not enough. We do need one more equation because there are two variables, two constants. Then you calculate y prime. After you calculate y prime, you substitute t equal to 0 again. So here is your y. Calculate y prime should give you negative 2 C1 and this, and then C2 and this, and let t equal to 0. So that gives us negative 2 C1 plus C2, which is negative 5. So you got two equations, two constant, two variables. Solve for C1, C2. So you get C1 equal to 3 and C2 equal to 1. So then your general solution in this case, y of t is equal to C13, so E negative 2t, and then E to the power of t. Okay, so that's how you solve. So we still call this is a particular solution, right? This is basically changing from general to a particular now, because it's based on a set of initial conditions. Okay, so that's a very simple example when you have two distinct real roots. So let's take a look at another example here. Okay, so this is one here is very simple, also real coefficients, constant. Characteristic equation, lambda squared plus lambda plus 0.25. So how do I solve this? If you have you have practiced a little bit, you'll be able to see that this side here can be written as lambda plus 0.5 bracket to the power 2. Right? Yeah. So that gives us just one solution, negative 0.5. This is the case we call that you have a repeated real roots. Right? So this is essentially square at here. That's what we call repeated, right? Yeah. Okay, if it's repeated, you look at your table. The general solution is C1 plus C2 times t, and then e to the power negative 5 t. Okay. So this question didn't give you any initial conditions, so then you don't have to go ahead and solve for C1, C2. Otherwise, you can solve for C1 and C2. Okay. That's case number 2, right? So I'm giving you an example for each case set here. Let's take a look one more example here. Okay. So let's take a look at this one here. So 0.4 y prime y double prime plus 0.4 y prime plus 9.04 y. Characteristic equation, okay, which is this. Now you do probably need a calculator for this one now, okay? By looking at it, doing a fraction, factoring this is probably not possible. So in this case, we get a lambda 1 and 2 equal to negative 0.2 plus minus j times 3. Okay. There's probably a digits here. Okay. Actually, probably not. Okay. That's an integer 3 here. Okay. So you get two complex conjugate roots. If it's two complex conjugate roots, essentially this is like alpha plus minus j beta. So alpha here is negative 0.2 and beta here is 3. So use the formula in your table. Your general solution of y is e to the power of negative, e to the not negative, what is it? E to the power of alpha t, right? And a times cosine beta t plus b times sine beta t. That's your general solution. So substitute alpha into it. Okay. That's the general solution. You can choose to one more step of simplification, that's fine, but you can stop here, and that's okay too. So 1, 2, 3 different cases. All right? Yeah. Okay, so I want to show you one more example, which actually will lead us into the next topic. So let's take a look at this second order ODE. There's no y prime term. There's only y double prime plus omega square y. Right? So very similarly, we get our characteristic equation here is lambda square plus omega square equal to 0. And the solution for lambda, what's the solution for lambda here? And then j times omega. Okay? Yeah. It's a complex number. Okay? So then, according to my formula, alpha is 0, beta is omega. So your y should be a times cosine omega t plus b times sine omega t. Okay. Okay, so why do I do this? Okay. I want you to compare this example with the previous example. Okay. So this example has two complex conjugate roots. But in this example here, what do you expect the y going to be as t approach infinite? As t, yes, it will be 0, right? Because this is exponentially decaying. But this term here is just going to be constant oscillation, right? Because a cosine 3t plus b sine 3t, as I said, you can always write addition of two sinusoidal into a single sinusoidal signal with a different amplitude. Okay. But irrespective of what, this one here meaning you have a constant up and downs, right? Oscillations. So in this example here, you do have a coefficient set here. But in this example, you don't have anything, just the omega square. And that gives you a solution like this, which resulted in a constant oscillation. Okay? Yeah. So how is that? So I'll give you an example to explain. Basically, I would call this, I'll quickly go over this. Okay? I would call this as application to harmonic oscillator. And sometimes we call this as a free vibration. Okay, free vibration. So here's the idea, okay? Here's the idea here. First, okay, let me go back to the mass spring damper system. By this time, I will only have a mass and a spring without the damper. So just the mass and the spring. Okay, let's suppose that you have a mass, you had a spring, and then you have the motion indicated by the x. But in this case, there is no external force. Okay, no external force. So if you model this system, you get mx double dot plus k times x equal to 0. Right? You get this. Okay. And this is the model of the system. Then I can actually rewrite this, right, or solve this one here. So this case here, we're going to categorize it as so-called undamped system, because there's no damper. Okay, that's why it's going to be an undamped system. So what is this characteristic equation? Characteristic equation here, you can write it m lambda square plus k equal to 0, or lambda square equal to positive negative j and k over m. Okay, k over m. So that equation here is the same as x double dot plus k over m x equal to 0. Right, if you divide it by m for both sides. So this equation is actually what? The same as what? The same as this example here, isn't it, right? Same as this example. So if you look at this example here, when you put an omega square here, the solution is what? Is A cosine omega square, B sine omega square. So meaning the Y will oscillate at what frequency? At this omega frequency, okay? Which is basically the square root of this term. So now I have K over M at here. So if I get my solution out of this equation, my x of t, okay, is A times cosine K over M t and plus B times sine K over M t. Okay. And that's equivalent to another constant times cosine omega. Let's call this omega n minus a phase. The omega n at here is basically the root K over M. Right? That's the frequency of the oscillation. And we call this is the natural frequency. Okay, this is called a natural frequency. So you have heard a lot about vibrations, and you probably have heard of a natural frequency. This is basically an example of what a natural frequency is. Okay. It's determined by the system parameter. It's like the system's characteristic. When you have this system here, it will vibrate at this natural frequency. Is that good? Okay, so that's called undamped response, right? Undamped response. Okay. If you have initial conditions, you can find the A and B value, and you can always plot this out. So the plot of this will be more or less like that. So this is your x of t. So there is a constant vibration at here. No damping, it will just keep vibrating, right? So far so good, right? So I'm relating the second order ODE's math with kind of real applications. I mean, if you have RLC circuits, okay, and you RL circuit in particular, you actually will have a similar second order equation, okay, undamped. So I guess that will lead us, because this is undamped, there's only no damping here. So that probably will lead us to the next one. How about if we have damping? So if we have a damper, right, then what's going to happen? Okay. So the second one here, let's call this is a free vibration with viscous damping. Because the damper we consider is a viscous damper. Okay. So that's the damper. As we said, if you look at the hinge of the door, you have this kind of damper system at the hinge, okay, to prevent the door from shutting or opening too fast. And for this equation right here, okay, and you can write down the equation of motion. So mx double dot plus bx dot and plus kx equal to 0. Okay, that's a second order ODE. So this is very much like in the table that I gave it to you. This is like A, B, C, right? In the table that you have there. Okay. But you can always divide it by m to normalize the first term to be 1, the coefficient. Okay, so for this particular one, you can solve for characteristic equation. So characteristic equation will be, right, m lambda square plus b lambda plus k equal to 0. Very much the same typical second order constant coefficient linear ODE, homogeneous one. Okay. Then you solve for lambda. So lambda can be solved to get 2 answers. Okay. So you get 2 lambda solutions. And this will actually basically fall into the table based on the values of m, b, k. So you could have 3 different cases. 2 real roots, 2 repeated roots, and then 2 complex conjugate roots. It's all up to the values of b, m, k, right? Yeah. So when it comes to the physical system, okay, we do the following things. We will define omega n as k over m, just like the case number 1, the undamped. This is what we call its a natural frequency. Okay, so this is still the natural frequency. But because now you have the damper here, okay, so we typically call it undamped natural frequency. Okay, so there is another one called damped natural frequency. Okay, but anyway, so that's your omega n. Okay, and then we're going to define another one called critical damping constant. Okay, so let's call this as BC, and that's square root 4mk. So this term 4mk, square root 4mk, is defined as a called critical damping constant. And the last definition, okay, introduce another symbol called zeta. Okay, so this one here, you write like that. No, sorry. Just one twist, okay, called zeta, Greek letter zeta. So this one is called damping ratio. Okay. And damping ratio is defined as damping constant, which is the B, right? Damping constant given by the damper B, and divided by the critical damping constant. Yes. This one? It's called a zeta. So you write it like that. Yeah. I might pronounce it wrong. Zeta or eta, because there's another one called this. There's the 2 twist. Yeah. Anyway. Yeah. Okay. So trust me, here we're not introducing any new things. We're basically kind of renaming some new variables here, okay, out of the given constants. So, okay, I'll stop here and then I'll continue in the next lecture. Okay. Any questions? Okay.